In the previous lecture, we have discussed regarding a solution of one-dimensional wave equation, which represent as this equation, that is yxx is equal to 1 by c square ytt. And the solution of this equation we have achieved is this, that is known as D'Alembert solution. Now here in this lecture we are discussing a property of characteristics. So this equation x is equal to x minus c, t is equal to some constant, and x plus ct is equal to some constants are known as characteristic of the equation of this one-dimensional wave equation. They are the characteristic of that. Now if you change this function f and this function g, then according to that the solution will be changed. So in that we have the first situation that we have, it is characteristic are carried of discontinuity. That means if the characteristics carried the discontinuity, so let us consider the initial shape of a string. If you consider a string and its initial shape we will consider be a triangular, that is given by the equation f of x is equal to 0 if your value of x is between minus infinity to a, x plus a, it is between minus a to 0, a minus x if it is between 0 to a and 0 if otherwise, that means it is from a to infinity. So this is the condition for y of x 0 is equal to f of x. See, in the previously we have seen that the solution of this one is this under the two conditions, that is y of x 0 is equal to f of x and yt at x0 is g of x. That means initially the displacement is this function f of x and the velocity is g of x. So here is this the function we have, and we'll consider the velocity. Suppose that the velocity is given by yt at x comma 0 is 0, that is the function g is 0. And what will be the graph of this function? The graph of this function is look like in this, that is I have said it is initial shape of the string where t is 0. So this function actually we have here from minus infinity to a, so this point is, this side it is 0, this a to infinity it is 0, minus a to 0 it has this function that is x plus a, and from 0 to a it is a minus x. So that is this graph of the function you have. So at t equal to 0 this is the initial shape you have, and then you release a string. So what is the situation you have here? This function is actually not differentiable at 3 points. That means it is not differentiable here, it is not differentiable at this point, and it is not differentiable at this point, because there is a corner in this string you have. So that is the situation you can observe, and we just see that what will be the solution of this function. As we have, the solution is look like this, that is y of xt is 1 by 2 f plus f, that is x minus ct, f of x plus ct, and g is this. Since this g is 0, so I'll say this is the equation number 1, and I will say this is the solution, will be equation 2. So we'll say that from equation 2, we get the solution of wave equation is y of xt is equal to 1 by 2 f of x minus ct plus f of x plus ct. Now we observe that this function f is continuous. We note that f is continuous on minus infinity to plus infinity. But it is not differentiable at 3 points, that is 0, a and minus a. That we have seen. At minus a it is not differentiable, at 0 it is not differentiable, and at a is not differentiable. Hence, I will say this is a figure 1. This will be the figure 2. So hence, the initial strip or shape of the string, see the figure 1. In the figure 1 it is already says, and it has peaks at these points. That means it's changing its value at these 3 points, because then it's changing from 0 to this value, then this value is going decreasing, and then it's from this to that, it is have this. And we shall see how this ins are propagate. That means how this will be affect the further situation you will have. So let us observe that the initial strip, initial shape divide into 2 equal halves. That is, the first half is this one and the another one is this. And it's each travel with the speed of c in opposite direction. So actually, when you will have some string, and if you can release that string, if it is initially, this is the situation. So you have a string like this. So what we'll do is you pick up this point and straighten. So the string will become like this. So this is the situation, and then you release the string, and then what will happen to that string? What is the wave you will have? That you need to understand here. So it is actually the shape of string will be like this. When it is p equal to a upon 2c. When t is equal to a upon c, then the waves like this, and when t is greater than a upon c, then it will have a wave. 2 waves goes on the other side. So this way the helms is goes when a time goes. So we observe that the initial shape divide into two equal parts, two equal hills, and each travels with a speed of c in opposite direction. In general, there are 6 jumps in a slope. In general, there are 6 jumps in the slope. So you can just observe what are that 6 jumps in a slope. So here the slope is 0. Here the slope is something, then the slope is changing, then it will change, and then it will change. So here initially there are 4 slope changes is there, and here it is one slope change from here to there, then from this point to this point it is the same shape, and then from this to this. So 1 to 2, 2 to 3, 3 to 4. Here there are 5 shape changes is there. Here you will have 6 changes. That means from here to there it will change slope. From this point to this point it will change. From this to this it will change. From this here to there, and then it will go going constant. So these are the locus of 6 points where the jump in a slopes are as follows. So these 6 slopes will be changing. So the locus of this 6 points where there is a jump in the slope are as follows. So let us see what are that points you will have. So just observe that x minus ct is a, that is the locus of p plus, that is here. We'll start with this. This is the point p plus, that is x minus ct is a. Then at a plus, then at q plus, then it will change to p minus, then p a minus, and then q minus. So at this 6 places the slope will change. That is locus at p plus. X minus ct is 0, that is locus of a plus. X minus ct will be minus a, that is locus of q plus. Then it is x plus ct is a, that is locus of p minus. X plus ct is 0, that is locus of a minus. X plus ct is minus a, that is locus of q minus. See the figure. Okay, so this is the situation you will have for changing its slopes with a different situation. Now the second case, that means we are discussing the property of characteristics. In that we have a second case. So in the first case we have seen that if the characteristics carries a discontinuity, then what will happen? The second one is the characteristic determine the solution uniquely only if the data is prescribed on both of them. That means a data will be described in both the situation. That means for the small g and capital G, both the data is given to, you know that, then you can able to describe what is the solution is. So as we know that the general solution for the wave equation, we'll have consider the general solution of a wave equation, that is y of xt, or in terms of xi, we have written its capital F of xi plus g of eta, where xi and eta we have calculated is capital X minus ct plus g of x plus ct. So this is the solution which we have. If I take the differentiation of this with respect to t, then will gives me yt, which gives the derivative of this with respect to t, which is f dash x minus ct, and then derivative of x minus ct will gives me minus c, plus g dash x plus ct, derivative of x plus ct with respect to t will gives me c. So by chain rule we can have this. Let the data be given on xi equal to 0. Xi equal to 0 means one of the characteristic is 0. That is given. That means y of 0 eta, that means here if I substitute this xi and eta where xi is 0, we'll have given it is g of eta, small g of eta. So therefore we can have y of 0 eta from this equation 3, y of 0 eta is f of 0 plus g of eta. But y of 0 eta we have assumed it is g of eta. So that's why this will gives me g of eta equal to f of 0 plus g of eta. And if I substitute this value, that means what will be the, this will gives me g of eta. G of eta will gives me g of eta minus f of 0, where g is a known function, f still we need to calculate. So therefore from 3, again by putting this value into 3, putting value of g of eta in 3, we get y of xi eta is f of xi plus g of eta, but g of eta we have seen it is small g of eta minus f of 0. Let me take differentiation of this with respect to t. If I can differentiate this with respect to t, then we'll have yt at xi eta. All these three are functions of t because xi and eta are the functions of t. So the first thing, that is this quantity will gives me f dash xi, and what is the value of xi we have taken here? It is x minus ct. The derivative of xi will gives me minus c plus g dash of eta. The derivative of eta with respect to t will gives me c, because eta is equal to x plus ct and xi is x minus ct. And derivative of this f will gives me minus f dash of 0. Now if I substitute putting xi equal to 0, that means yt at 0 eta will gives me minus c into f dash of 0 plus c times g dash of eta, and this function f is a constant with respect to t, so that derivative is 0, so this term should not be there, so only you will have this thing, and hence yt cannot be prescribed arbitrary when xi is 0, or we can say from this, and hence yt cannot be prescribed arbitrary on xi equal to 0. Moreover, we do not have any condition to determine f, which is left arbitrary, and thus the solution is not unique. So here what we have considered only one condition, that is we know only about the g function, we don't know what is the capital F. So that's why if you can do this process, the f which we have, it is an arbitrary and it will not lead to a unique solution. So we do not have any condition to determine capital F of xi, which is left arbitrary, and thus the solution is not unique. The solution will not be unique in this case. So the characteristic curves such that if the data is prescribed only on one of them, the solution will not be unique. So if you want the solution will be unique, you need to have both this condition. That means on both the characteristic, the values should be given. So the characteristic are curves such that if the data is prescribed only on one of them, then the solution is not unique. That is the conclusion we can make. However, we describe the data on both the characteristic. If we prescribe data on both psi equal to 0 and eta equal to 0, the solution is unique. So if we have on both this characteristic, if it is given data is there, then the solution should be unique. And let us see this is by. That means if y of 0 eta is, we have given xi of eta, and y of xi 0, that means that is a xi is 0, here it is eta is 0. It has f of xi. Then we have f of xi eta. F of xi eta is, we know it is capital F of xi plus g of eta. This is actually the equation 3 you have. Now here you can substitute 0 eta, that means xi is equal to 0. This is gives me f of 0 plus g of eta. But why 0 eta is g of eta, so that is equal to g of eta. So we'll have g of eta is equal to capital F of 0 plus g of eta. We'll say this is equation 4. Again, by putting here in this equation eta is equal to 0, we'll have xi 0, and that is the value is f of xi is given. We'll have it as capital F of xi plus g of 0. So that will leads to capital F of xi is equal to, small f of xi is equal to capital F of xi plus g of 0. This is equation number 5. If I substitute this value of f of xi and g of eta from equation 4 and 5 into the equation 3, therefore we'll have y of xi eta is equal to f of xi minus g of 0, that we can get from the value of this f of xi minus g of 0, and from value of g of eta is g of eta minus f of xi. So it is plus g of eta minus f of 0, and that will leads to f of xi minus plus g of eta minus small f of 0. Why? Because small f of 0 is same as small g of 0. Thus, the solution is uniquely determined for both these characteristics are given. So thus, because this f is known to you, g is known to you, and this f of 0 is also known to you. See why this has come, because you know that y of xi eta is capital F of xi plus g of eta. If I substitute 0 0, that means y0 eta 0, that is f of 0 plus g of 0, and y0 eta 0 will gives me this value, and this is actually y of 0 0. Y of 0 0 as per the given condition, that is y of xi 0 is f of xi. If I can substitute, then if I put xi, then it is gives me y of 0 0, that is f of 0. So that's why y of 0 0 is f of 0 plus g of 0, and that is exactly the small f of 0. So that's I have substituted here. So thus what we can say is the solution is uniquely determined if the data is given on both the characteristics. If it is data is given on the both the characteristic, the solution will be unique. Now the next, the property third, that is the C part of this, it's saying about the domain of independence. That means characteristics are determined the domain of independence. Domain of dependence. And the range of influence. So here also I need one figure in that will understand what you mean by this domain of independence and the range of influence. So we'll have this is the point A and this is the point T and this is the point B. So we'll have this is the point P which is x1 T1. This is the point A and B. This is your x-axis and this will be your y-axis. This line, it is x is plus ct is equal to x1 plus ct1 and this is x minus ct is equal to x1 minus ct1, and this inside this triangle, this is actually the domain of dependence. And this point is x1 comma 0. So, and what is the range of influence, that also we can see. So let P of x1 comma t1 be any point where t1 is greater than 0. Now from the solution 2, that is this solution we have discussed, the first, that is the solution 2 which we have. If I can write down the solution at this point, that is x1 y1, that I can write down here. It is y of x1 t1 is equal to 1 by 2 f of x1 minus c t1 plus f of x1 plus c t1 plus 1 by 2c integration x1 minus c t1 to x1 plus c t1 g of z dz. Now at this point f of x1 t1, this is 1 by 2 small. You can see in this figure we have said this is the point, it is A, and this is the point B. We have B, that is exactly the x1 minus c. So this point is actually x1 minus c t1 comma 0, and this point is x1 plus c t1 comma 0. So this point is A and this point is B. So that is f of A plus f of B plus 1 by 2c integration from A to B g of z dz. And hence y of, this is the y of p we have, that is this point. Y of p, if you want to calculate this y of p, it depends on the data which given on this line segment, that is PA and PB. That means whatever the data is given on this line segment AB, if you know, then we can able to calculate what is this YP. Because if you know this A, if you know this B, and if you know this integration, then and only then you can able to calculate. So that's why this region, which is between the segment AB, it's called the domain of independence. So what we can say, hence YP depends only on the data given on the line segment AB. See the figure. For this reason, the segment AB, it's called domain of dependence. For P. And the segment AB is determined by two characteristics passing through T. If you want to find out that segment, the segment is determined by the two characteristics passing through P. In fact, any 2 points lying on inside this triangular region, any 2 points which are lies in this triangular region, bounded by two characteristic segments, that is AB and this two characteristic segment, will have domain of independence within the segment AB. So this is the definition of domain of dependence. Now what is the range of independence? So for that I need to draw a figure. So let us consider this is your x-axis and y-axis. You consider this is the characteristic segments. This is x plus ct is equal to x1, and this is x minus ct is equal to x1. This is the point which I say it is x1 comma 0. This is your x-axis and this will be your y-axis. And this region which is here, that is called range of influence of A. So the data at x1 comma 0 on OX axis will influence means all this data which will depends on this point A. That is meaning by influence. Influence the value of y of xt at point P lying in the region bounded by the two characteristics passing through A x1 comma 0. See the figure. This region, it's called a range of influence of the point x1 comma 0. And we observe that any point P which lies in the sector has a point A within the domain of independence. So this is the characteristics that we need to discuss for a solution of vibrating string, vibrating infinite string. So in the next lecture we'll discuss regarding the vibration of semi-infinite string. Semi-infinite string means we have one side, it is block now. So we have one string which is attached on the one side, and other side it is infinity. So that's a string is known as infinite string, and we'll put some waves on or some extra force onto the string, and to calculate what will be the position of a point at given x and given time t. That we will discuss in the next lecture. So if you have any questions, you can ask.